Hello, this is the design portion of the circuits project, and I have designed a circuit that will turn an LED on and off using a switch. It will change the brightness of the LED via a potentiometer, and using a capacitor, it will power the LED when the switch is turned off. Moving on to the analysis portion, we will do KCL at node B. So the current coming in is equal to the current leaving, use Ohm's law, and eventually get it to the standard form for a single order differential equation. From that, we will find the homogeneous solution and the particular solution. I have made the assumption that as t heads to infinity, the voltage at B will be 2.2 because that is the voltage drop that is needed across our LED. That will give us C2, and then we can make another assumption that as t equals 0, the voltage at B is also 0. This gives us our C1 and C2 and our entire equation for the voltage at B as it relates to time. From that, we can find the voltage at A by taking the voltage supplied by the battery and subtracting our voltage at B. This entire analysis was done with the assumption that the potentiometer is at 0 ohms. When we increase the potentiometer completely to the 10 kiloohms, the lambda value for the differential equation drops from 0.863 to 0.0157. What this does is it increases the time to fully charge the capacitor, but it also takes much longer for it to discharge as well. From this, we can determine the current from the battery, and that also changes with time. Now we can see that at t is 0, the initial current will be 18.19 milliamps, and as t is infinity, we will have a current of 14.96. We will verify our results by using the conservation of power. P is equal to IV, so what I did was I took the volts supplied by the battery and multiplied it by the I equation that we have gotten above. We will do this as t is equal to infinity. We can do this for any t value and should get the same end result that power is conserved. So you can see as you sum these together, you get 0 milliwatts, aka there's a conservation of power. One thing that I will note is we saw that the power from the LED is 32.9, and that does not exceed our max power dissipated for the LED, which is 170 watts. The typical continuous forward current for the LED is 20 milliamps. We have about 15 as t goes to infinity, which doesn't affect our analysis too much. And next we will move on to the creation of the circuit. This is the prototype to the circuit that I designed. This is the positive of the battery. It goes through a wire that hits the switch, then goes to the 680 ohm resistor that then, this would then be node B, and it branches off to the capacitor, and then the other part goes to the potentiometer and the LED that is then connected to the ground. We will now check some values to test whether our analysis of the circuit is correct. I'll turn on the LED. You can see that it lit up. Now, my capacitor may not act like a normal capacitor because I may have put it in backwards a couple of times, and after looking online, I can see that would probably have some effect on the way it behaves. We are measuring the voltage across the LED as of right now, and as you can see, it's about 2.03, which is a little shy of how we predicted the LED would act. We predicted it with a 2.2, and we can see that this difference is also seen across the resistor. We are measuring the voltage drop across the 680 ohm resistor, and as of right now, it is about 10.23. and this reflects the voltage drop that was across the LED as well, which was 2.03, which both should add up to around 12.3, 12.4, which is what the batteries are outputting. We're measuring the current that goes across the LED. As of right now, it's at about 19, which is initially about 4 milliamps higher than what we predicted. And I believe this is because of my my capacitor. When I was doing tests before, it was hovering around 15 milliamps, which is what it was analyzed to be around.